Okay, we will start the channel coding module of digital communication system. Previously, we have studied the baseband signaling and pulse shaping techniques for baseband signaling, and then we learned the equalization techniques for baseband equivalent model, and then we learned the bandpass signaling or bandpass modulation, in which we studied the coherent and non-coherent version of bandpass signaling. So now we start the channel coding module. The channel coding module also works with the baseband equivalent model, and then you can apply it for the bandpass model as well. So channel coding improves the error performance at the cost of increased bandwidth. So we learn some basic concepts. So the initial of coding is from waveform coding, and the waveform coding is the antipodal signaling and orthogonal signaling. Antipodal signaling is just the inverse of the signal. For example, if you are representing an antipodal signal, so it is plus minus e under root symbol set. So orthogonal signal set is in fact is time shifted version of the pulse t by 2 time, and the other pulse with a 0 starting time. So these two pulses are orthogonal. And if we want to try the orthogonality, so we just take the cross correlation of these two signals, and the result will be 0 for the symbol duration, which is t. For orthonormal basis function, we need to normalize it by the, say, symbol energy. So the product of these two energies under root e is E, and when it is normalized by E, so its value is 1 for I not equal to I equal to j, and 0 otherwise. Here the energy of the symbol is the square of the signal, and integrate it over the bit duration will give us the signal energy. Pictorially, you can see these two waveforms. The antipodal waveforms have the distance of 2e under root. So this energy is 2e under root. But in case of orthogonal, so this distance is 2e under root. So this is the distance properties of antipodal and orthogonal signals. So by waveform coding, we improve the performance of the digital communication waveform array. So we have the orthogonal and bi-orthogonal arrays. So we want to minimize the cross correlation coefficient between the symbols of the M array symbol set, and minimum possible value is -1. So it is also possible to make all cross correlation coefficient equal to 0, just like in orthogonal. So the cross correlation between two signals is a measure of the distance between the signal vectors. So The cross correlation is a measure of the distance between two signal vectors. How it's possible that you take the cross correlation with one symbol and then you take the cross correlation of the same symbol with another one. So this will give you the distance properties in terms of cross correlation coefficients. So in coding, we have the cross correlation coefficient measures by number of similar bits minus number of dissimilar bits divided by the total number of bits. For example, if there are 8 bits in the sequence and we have 4 similar bits and 4 dissimilar bits, so it means that the cross correlation coefficient value is 0. So it means that these two sequences are different and they are orthogonal. And if the value is equal to 1, it means this is the autocorrelation with the same symbol, because 8 bits are similar and 0 bits are dissimilar, and 8 by 8 is equal to 1. Now we learned that how we generate the orthogonal codes. We use the Hadamard matrix. Hadamard matrix have a principle that you have started with a seed of 0 and you replicate it horizontally and vertically with the same bit and invert the bit in the diagonal direction. So in that way you can generate the first Hadamard matrix. So these two sequences are orthogonal, and if you how can you check it? Because you check the number of dissimilar bits 1, and number of similar bits 1, and the total number of bits 2. So 1 minus 1 divided by 2 is equal to 0. It means that these two are orthogonal sequence. So this will help to represent a data set of 0 and 1. So in order to represent a data set having 2 bits, so we need Hadamard matrix 2, and this will be generated from Hadamard matrix 1. How we can generate it? We take the Hadamard matrix in horizontal and vertical direction and we invert it diagonally. So you can see the case here that horizontally we have the similar pattern, vertically we have the similar pattern, and diagonally we have the inverted version of the bit. So these represents the orthogonal sequence of 4 different symbols in the data set. So these are represented by 4-bit sequences. Similarly, we use Hadamard matrix 3 for the representation of 3-bit data set having 8 symbols. You can check the orthogonality by using this formula of correlation coefficient. So this formula is used to check the orthogonality of the sequence. All these sequences are orthogonal to each other. So this is the way that we generate the Hadamard matrix of any type, way of any order, and these are orthogonal in nature. Every sequence generated by Hadamard matrix is orthogonal to the other sequence within this matrix, and it is a square matrix. It is always a square matrix, having order 2 by 2, having order 4 by 4, having order 8 by 8, and that order is 2 raised to power 3. So all these matrices are square matrices. So because of the orthogonality, we can say that the probability of symbol error is just like same as in case of MFSK. So because all the sequences are orthogonal, so it is just like the error performance is same as we have in case of MFSK. So if you see that this part is in fact is the binary orthogonal signaling, and for M array we have m minus 1 into this Q function error probability. So symbol energy is in fact is k times of the bit energy, and same the duration of the symbol is k times of the duration of the bit. So you learn in the previous lectures as well. So biorthogonal sequence have reduced the number of bits, but still can achieve the better performance compared to the orthogonal sequence, because in this case half of the sequence are antipodal. You can say that we have this sequence of 4 by 4 is orthogonal, and the inverted sequence of this is also orthogonal. And these, if you see that these have the antipodal characteristics. These are the antipodal characteristics. So you can see that the every symbol has its antipodal in the sequence, and there is 4 by 4 orthogonal and 4 by 4 orthogonal sequence. So we are using one additional bit to transmit the equivalent code word, and that code word has the orthogonality and the antipodal characteristics. So 3 bits are represented by 4 bit in this biorthogonal sequence. So we have the property that that is the same for antipodal. If you have the autocorrelation of any sequence, that is 1, and if you have the sequence with a distance of m by 2, then it means that in case of 2 raised to power 3 bit sequence, so you have 8 possibilities, and every 4th symbol is antipodal, and that is what is better, what makes it better from the orthogonal one. So this is the, because it has the minimum cross correlation coefficient for half of the symbols, and here we have 0 for m not equal to 2. So if we see the symbol error probability, so the orthogonality is for m minus 2 symbols, and plus we have the probability of antipodal signals. So this is the total symbol error probability. So that's the upper bound for probability of code word error. Waveform coding system, in which we are generating the waveforms. M waveforms are generated for m is equal to 2k possible symbols, and these waveforms are in fact 0 and pi shift, have 0 and pi shift. So because we take first from this symbol, and depending the phase either is 0 or 1, and depending over the phase of the next is 0 or 1, the corresponding phase is 0 or pi. So here in that way we generate for all the possible values from k bits or 2 raised to power k bits or m generators. What I mean to say is that in the code word or in the coded waveform, we have in fact m bits. We have m bits, or we have m waveforms. So, for example, you have seen previously that to represent k bit, we are using m waveforms. For orthogonal case at the receiving side, we generate the m waveforms, and after multiplication with the carrier, we have multiply with the waveform set and integrate it over the bit duration, and then we take the sample, and then we go to the decision stage for all these bits. So here you can see that the symbol duration is k times tb. So this is how we perform waveform coding. Now there is a concept of error control. So we study the types of communication. One way is that we have the one-way communication, and one way we have the two-way communication with one pair. So either in one direction. So this is half duplex, or simultaneously both-way communication or over two pair is full duplex. So this is the type of communication, and now we study the error control mechanism. One is the automatic repeat request, and one is the forward error correction. So in communication, where we can retransmit, so we use automatic repeat request. So if the errors comes, we request the transmitter to resend the data again. And forward error correction means that we send some redundant data with the actual data, and if the error comes, so the redundant data helps to recover the actual data. So forward error correction is used in satellite communication, because the two-way uplink and downlink communication is 540 millisecond uh, delay, so that is not possible to retransmit in that case. So ARQ is better in a sense that it needs little redundancy. ARQ is sometimes not possible if a receiver channel is not available or the delay with ARQ would be excessive. So the retransmission strategy is not conveniently implemented. The expected number of errors without correction would require excessive retransmissions. So in ARQ, we have stop and wait ARQ. So that is the oldest mechanism in which the communication stop when we have the erroneous message, and when we get the correct version of the message, then we restart the transmission again. So it means that it's not the proper way because it stops the communication. So we use continuous ARQ with pullback. So it is when the negative acknowledgement comes from the receiver, so it starts the transmission again from the point where the errors comes. So it's also not proper. So to overcome this, we have continuous ARQ with selective repeat. So in this, we have the negative acknowledgement and the selected frame is only retransmitted, and that acknowledgement is sent, and we continue from the next symbol. So that is selective repeat request is better than other methods. Now we study the coding part. So this coding is in fact is used for forward error correction. So they have some structured sequence, have some redundant data. So there are three different types. So the block codes have the generated matrix and the parity check matrix at the receiver to decode the data, and have a cyclic version of it. Convolution codes have a decoding method based on the sequence estimator. So the convolution codes is in fact encode the data based on the previous bits. So we decode the sequence instead of decoding a single bit. Turbo codes use maximum likelihood decoding method. So it is also based on the information we have previously transmitted. So the turbo codes have an iterative decoding method. So turbo codes are very fast. So the turbo codes are used in most of the channels where low bit error rate is required. So the reliability and the robustness of turbo codes is well known. So first we learn the information that, for example, we have a k-bit data block. So we encode it with n-coded bits over the channel. So n minus k are redundant bits. It may be the parity bits. So the parity bits carry no information. These are the redundant information which helps to recover the data. So the redundancy of the code is the redundant data divided by the actual data. So that is n minus k divided by k. So here you can see that that is n minus k by k. And the ratio of the database to the total weights is the code rate, which is k by n. Normally we represent the code with the coded weights n and into comma k. So this is the way of representing a code that we normally represent by the first we write the number of the coded bits and then we write the number of the actual bits. So this is n by k code or n comma k code. So the beginning we have the parity. We set the parity as we set in the ASCII characters. So there is a 1-bit parity and that may be even or odd. So in even parity, the total number of bits in the parity would be even. So the zero parity means that there are two ones and one means that there is three ones, and by adding one means that they have even number of ones. And here it is one because there is single one. So this is the even parity example. Similarly, we set the odd parity. If we set the odd parity, here we have the one, here we have zero, and here we have zero. So this parity is checked whether the data is correct or not, and then we ask for retransmission. And so it can be implemented over a block of data with a code rate of m by n. For example, we divide the data into rectangular blocks. So we calculate the parity in both direction. So one is the row-wise parity. So the row-wise parity is the even parity, and we have the column-wise parity. It's also the even parity. So we have additional one column and one row for parity. For row-wise parity, we have an additional column, and for column-wise parity, we have an additional row. So in fact, the actual data is of an order m by n, and we have an coded data order of m plus 1 into n plus 1. So this is in fact is the code rate k by n of the rectangular code. So there are several trade-offs between error correction coding. So in generally, there is unhidden property, which is the bandwidth, which cannot be visible here, but you can generalize it that the error performance of the code can be achieved by increasing the bandwidth of the transmitted data. So with so if I want to say that if I want to transmit the actual data with more number of bits, of course I achieve the better error performance, but in fact I am increasing the bandwidth. So you can see that if we move from A to C, so the error performance from 10 raised to power minus 2 is improved to 10 raised to power minus 4 at particular 8 dB. So you can say that this error performance is achieved uh, at the cost of bandwidth. Similarly, if I want to see that the 10 raised to power minus 6 error probability of bit error or error performance is achieved with less transmitted power, which is 9 dB compared to 14 dB. So how much gain it is? It is almost a gain of uh, 5 dB. So 5 dB gain is a very good achievement. So that is possible in the power limited regime when we have the limited power, limited transmission power. Of course, when we are transmitting from mobile, so we have the power concern because we are transmitting uh, at higher power will deplete our battery sharply or fastly. And also there is a trade-off between data rate and bandwidth. So we can go here up. So you can see that this is in fact is the data rate, which is improved, and that data rate can be achieved at the cost of higher bandwidth. So, and also there is a trade-off between capacity versus bandwidth. So this is the case. I give you an example of CDMA. So by increasing the code division multiple access, because in this we are using orthogonal codes for transmission, and orthogonal codes increase the capacity tremendously at the cost of higher band. In fact, we are using the code diversity as well. So usually in digital systems, we are exploiting the frequency and time diversity, and in CDMA, we are exploiting the diversity of the orthogonal sequence. So these orthogonal sequences are recovered due to the orthogonal nature of the sequence selected for each user. So now we start the linear block codes. Why we call these linear block codes, we learn later. But there are some addition and multiplication rule, which is set for binary communication. And we have the code vector space. Code vector space is in fact, for example, there is 2 raised to power k bit sequence. So we want to encode it. So we need the number of code words is the same. So it means if they are 8, so, and we have the code word of length n. So it means I need 2k code words from this larger vector space. For example, it is 2-bit, k is 2-bit, n is 4-bit. So it means 2 raised to power 4 is 16, and 2 raised to power 2 is 4. So we choose 4 codes from this 16 combinations. And for example, if I choose these 4 codes from this 16 combination, what is the criteria for that? That they have closure property over addition. It means that if I sum up the first 2 code words, so what will happen? So that sum will be another code word in a vector space, which is that code itself. If we have the exclusive OR, it is not addition, it is in fact exclusive OR. By exclusive OR zeros with any of the code, it's the code word itself. And if I sum up any of these 2 code words, so this will be that code word. So usually if you know the set theory, so this is the closure property over addition. So also this is the criteria for selection of 4 code words from this 16 combination, that they must satisfy this criteria. Also, there is all 0 vector in the vector space. So that is the 2 important thing, but really it's some hit and trial method for the selection of these 4 out of 16 code words, because we cannot exactly say that how we select this. For example, here we have the selection criteria that we have choose the minimum distance, a distance of 4. For example, if it is 0, so it is 4, it is 5, right? It is 5, and it is 8, 2, it's 10, and it's 16. But it's not the general rule for it. I mean, it's if it is 15. So 0, 5, 10, and 15. You have chosen it. So I mean, you have set the criteria that you choose a vector at some appropriate distance, equal distance. You have choose some at equal distance. So distance is 0, 0, 5, 10, 10, and 15. So it means that you satisfy at least some distance property here, but that is not the rule which is always satisfied. But in short, we can say that we improve the distance properties of the code words. And you know, when we increase the distance between the code words, we are minimizing the error. So, but it is not the general rule. I mean, it's basically a hit and trial that how you choose these 4 code words from this 16 vector space. But ultimately, we can say that we are increasing the distance between the uh, data space or the data space to the code word space. So we are improving the distance property of the code word space to minimize error. So this is how you can see that 2 raised to power k and tuples are improving the distance, and in fact, so improving the error performance of the signal space. So if we want to further improve the performance, we are going to keep on increasing the value of n. So it is in fact improving the distance, increasing the distance, and in fact improving the performance as well. So you are able to transmit at very low power by increasing the value of n. So that's what I am saying, that for 6.3 code, so we have actual message of 3-bit and a code word of 6-bit. Here the criteria is not satisfying. So we cannot find the rule that how we map this 6-bit code word into this message vector space. So this mapping is not set the criteria that we have maintained the proper distance between the code word. So these are just the mapping satisfying the 2 criterias which I have mentioned here, all zeros, and the closure property over addition. So it sets the criteria. You can just exclusive over any 2 code words and find another code in the code word set. Why it's so? Why it's so? Basically, you know, it's not just like a lookup table that we have a lookup table and we just check the mapping with a code word and we select it. For example, if we are considering a 3-bit sequence, so I agree with it that you can maintain this mapping. But for example, if you have 2 raised to power 92 mappings, so you cannot calculate the from the lookup table, or you cannot find from the lookup table. You cannot maintain it because the computation power is very high or the memory requirement are very high. So to overcome this, we use a generator matrix. Generator matrix is arranged in a way that I have choose some code words from this. For example, we have a generator matrix with all the code words. of VK. And these code words are of order K by N. So it's the K by N matrix. But in fact, I'm not choosing all the code words to generate the code word. First, we call it the linear block codes because it is the linear combination of the message. Secondly, we use the generator matrix instead of the lookup table because I showed you the example that for 10792 linear block code, so we cannot have the 92 entries of the lookup table. It's hard to manage it. So we reduce it to the generator matrix of order K by N. So in fact, I'm not doing it that I put all the K code words in the generator matrix. I select some code words from it. And all these code words are the linear combination of the message. That's why I am calling it the linear block code, right? So, for example, if there is a message in this example, here there is a message 110. 110. Okay, this is the message 110. So I have a generator matrix here. I choose only 3 code words, and with the help of these 3 code words, so these are not 8 code words. Here you look previous in this generator matrix, there are 8 code words, each having each having 6 entries. So it's not the way here. So how we do here? We use it. We use 3 code words because we have 3 message bits. So this 3 combination will multiply by this code words. So in fact, what I'm saying is it's really K by N because K is 3 and N is 6. So it's right, we are choosing K code words from this vector space, but these are not the all code words in the vector space. What I mean is that in fact these are this K is equal to 3. This K is not means that we have 8. I mean to say that this doesn't mean that this K is equal to 8. So, but it's order of 3 into 6. So here the order is 3 into 6. So which code words I have chosen here? So one is this, right? And one is this, and one is this. Why? Because if you see the message, so this is the first bit message. You say it, call it 4, and you call the weight of it 4. So it's the first message bit, and then you have the 2, which is the second message bit, and then you have 1, which is the first message bit. So these 3 message bits are important, and the corresponding code words are selected in the vector generator matrix. So all other are the combination of these 2. Either you have you make if you make 000, it means that you are multiplying each of these with 0. If you multiply any of the combination with this code word, you can have the corresponding weight by adding exclusive OR of this. So you can try it for all the combinations, and you can see that generator matrix will generate the code words for the corresponding vector space. So this code words is in fact is not the systematic code word. Systematic code word is the code word in which we append the actual data. And to append the actual data, we need some modification in the generator matrix. We split it into 2 parts. One, at the end, we append the identity matrix of k order. It means it is a square matrix of order k. So the overall order of the generator matrix is still n by k. Still n by k. But actually, in fact, what I'm doing, I'm splitting the n minus k part here and splitting rest of the k cross k here. So this will become k square matrix. So this will become parity matrix is k cross n minus k. So this identity matrix helps to append the message. So look at an example. For example, I give you I want to generate n code word bits of the code word, and we have k message bits. So it will be generated. The first parity bit, multiplying this row with this column, you will get P1 bit, or you will get U1 bit of the code word. And then you multiply first row with the second column, you get the second bit of the code word. And finally, n minus k bits are parity bits in the code word, and k bits are the actual message. So you can see here that we have the parity bits and we have the actual message bits, which are k bits appended at the end. Here you can see the 6x3 code that you have the message bits by multiplying 3-bit message with 3/6 k by n 3/6 matrix in which this is the identity matrix, and this last 3 bits are the actual message bit, and these 3 bits are the coded bits. So at the receiving, we need in fact the parity check matrix. So you know the parity matrix is like this, but the parity check matrix at the receiver will be the inverse of it. That you have in minus k p transpose. So this is in fact H is the parity check matrix. So first we write the parity check matrix in minus k into p transpose. So transpose of the message, and then we have the transpose of this, which is H transpose. So transpose of the parity check matrix is in minus k or p transpose, which is of the form like this. So first go back and see that how we can do it here. So this is in fact is the I3. So I3 will be converted to in minus k. So in minus k is also 3. So you have this at the top, and this message will be transposed. So this will be transposed in a way that the row will be converted here as a column. You can directly write H transpose, and this row will be this column will be converted as a row, and similarly you replace the columns with the rows. So here you can understand that what is the advantage of this is that the generator matrix, when multiply with the transpose of the matrix, the result will be 0. So also when you have a right code word, multiply with the parity check matrix, so the answer will be 0. So it means if GH transpose is 0, it means that you multiply any code word with H transpose, the answer will be 0. So this helps to find the error in the code word. Error is in fact syndrome means disease, and syndrome testing means that you diagnose the disease. And this means here that we check the error in the received code word. So if the received code word is the actual code word plus the error, so we multiply, we say that the received code word, when multiply with the H transpose, we get the non-zero value, which is the syndrome. So that syndrome is in fact receive vector is U plus error H transpose. So you have the two parts U H transpose plus E H transpose, and E H transpose is also the syndrome. And UH transpose, these two properties are used later on. The same vector when multiplied by H transpose will give you the syndrome if there is an error, or the error when multiplied by the H transpose, it gives you the same syndrome value, right? So here we use the lookup table. In that way, that we have the error patterns, and these error patterns are coset leaders. And with this error pattern, we have this complete coset. So error pattern is a coset leader. So similarly, it is able to detect 1-bit error. So 1-bit error is, and to some extent, to 2-bit errors and a few 2-bit errors. So we have all 1-bit errors patterns as coset ladders, and then we have the coset, complete coset. So what we will have, so first we will calculate the syndrome by multiplying the H transpose matrix, and then we have use the lookup table to find that which syndrome represent which error pattern. So which syndrome represents which error pattern. So we can set this table by multiplying this with H transpose, because we know that error when multiplied by this H transpose will give you the corresponding syndrome. So this is the corresponding syndrome. So multiply all these error patterns and calculate the corresponding syndromes. Now, when you receive a vector, so you multiply the receive vector and calculate the syndrome. So you also know that the receive vector, when multiplied by H transpose, will give you the same error pattern. So this is in fact is the same syndrome. So when you calculate the syndrome and you calculate the error pattern, so you just we find the error pattern from the syndrome value, then error pattern plus received vector, you add it or exclusive or it, so you will get the correct code word. Or you can have use this lookup table if you have for example this error pattern you find and the received code word is this, so you can just see the lookup table for the corrected code word or this corrected code word, or you just exclusive or these two to get this one. So this is the criteria you can have this calculation of syndrome and a coset and error corrected decoding here. So this is the example that the received vector and the H transpose metric and error pattern and the H transpose metric both have the same syndrome, right? So that's what I have said here, that error pattern and H transpose have the same syndrome and receive vector and H transpose have the same syndrome. So you got the corrected code word. Now see the lookup table. You add the receive vector at 2 stages. You need the receive vector at 2 stages. First one to calculate the syndrome and second time to correct the code word. So you calculate the syndromes. For example, you calculate the syndrome 100. So the first error pattern is 111. So that's the error pattern 1. So from these syndrome values, you calculate the error pattern 10000, and in the receive vector, you exclusive or this, you will get the corrected code word. And this syndrome S1, S2, and S3 are set with the help of these formulas we have calculated for the code words. So you see that the connections are of syndrome 1 are with R1, R4 and R6, and S2 is R2, R4 and R5, and S3 with R3, R5 and R6. So the distance, minimum distance is important because minimum distance is the number of dissimilar bits between the code words. And these dissimilar bits will help us to, that is called the minimum distance. And the error correction capability of the code will be d min minus 1 by 2. And error detection capability of the code word is d min minus 1. So these are the two examples. So you can try it. I will upload it on the Moodle and we will discuss it in the online session. Thank you very much.